Hey everyone, in this video we're going to talk about two new methods for solving quadratic equations. To motivate this idea, let's ask the question on what we do if a quadratic doesn't factor. For instance, the AC method is going to fail with the quadratic 2x squared minus 12x plus 14 is equal to 0. Let's shift gears and look at another example. The quadratic x squared plus 2x plus 1 does factor, but it also factors in a very specific way. It factors as x plus 1 quantity squared. Usually when a quadratic factors, we have something like x plus 1 times x minus 5, where the two factors are different. But this one actually factors as a perfect square, which ends up being a pretty nice quality. And this is the concept that I want to focus on because the process of completing the square is chasing this type of situation, namely the one where a quadratic will factor as a perfect square. So to give a little bit of a flash forward, we'll go ahead and tell you that the quadratic 2x squared minus 12x plus 14 equals to 0 can be rewritten as x minus 3 quantity squared equals to 2. Again, this is a flash forward. The whole purpose is to show us the end result, because what we can do is take the original quadratic and transform it into this perfect square equation, x minus 3 squared equals to 2. The reason we would even want to do this in the first place is that solving for x now becomes easier. I can take the square root of both sides and transform this into x minus 3 equals plus minus the square root of 2. And when I solve for x, I'll get the solution x equals to 3 plus minus the square root of 2. In other words, this is two solutions where each version is either an addition or a subtraction of the square root of 2 from 3. So this is the process of completing the square, turning the original equation 2x squared minus 12x plus 14 equals to 0 into x minus 3 quantity squared equals to 2. We solve for x not by using the zero product property like we did in the last video, but by taking the square root of both sides because the factored left-hand side is a perfect square, making this a legal move. So not every polynomial factors as a perfect square. The example in the middle of this slide, x squared plus 2x plus 1, automatically factors as a perfect square just because it's a nice quadratic, but not every single one of them is going to do this. Some polynomials don't even need to factor nicely, but completing the square is essentially the next best thing. How can I rearrange or transform this polynomial so that I do have something factoring as a perfect square with a non-zero left-hand side? So we're going to use the same quadratic, 2x squared minus 12x plus 14 equals to 0, and we're going to demonstrate how we transformed it into the equation x minus 3 quantity squared equals to 2. And this set of steps is formalizing the completing the square process. So with a quadratic equation, write it in standard form like we have now, and make note of all of the a, b, and c coefficient values. Here a is equal to 2, b negative 12, and c equals to 14. The first thing we're going to do is compute the quantity b over 2a squared. When we plug these values in and simplify, we'll see that we get an answer of 9. It turns out that the number 9 and the number negative 3 here, in other words the number I got before I squared that quantity, will both be needed. Put these numbers in the back burner for now, and let's move on to step 2. Step 2 says to take our standard form equation and move the constant term to the right hand side. So for us that will mean a subtraction of 14 from both sides, leaving us with 2x squared minus 12x equals to negative 14. Even though we always start quadratic equations in standard form, this completing the square process does have us putting that constant term to the right-hand side. The third step is the following. Whenever my a term is not equal to 1, like it is now, we are going to divide all sides by a. So since a in this case is equal to 2, we take 2x squared minus 12x equals to negative 14, divide both sides by 2 to get x squared minus 6x equals to negative 7. Again, we only do step 3 when a is not equal to positive 1. If, for instance, a was equal to negative 1, I would still divide all sides by negative 1. But here in our case, a again is equal to positive 2, so we divide all sides by positive 2, and right now we're with the equation x squared minus 6x equals to negative 7. Next we'll use the quantity that we computed in step 1. We're going to take b over 2a squared, which for us is a 9, and add it to both sides. So this is x squared minus 6x plus 9 equals to negative 7 plus 9. And once we add it to both sides and then simplify, we get the equation x squared minus 6x plus 9 equals to 2. Now that I'm here, do I put this back into standard form? No, absolutely not. This is exactly where we want it. That left-hand side now factors. The whole point of this term b over 2a squared is that I am adding exactly what the left-hand side needs to factor as a perfect square. Since the left-hand side has been engineered to factor as a perfect square, this actually comes with a formula. The left-hand side will always factor as x plus b over 2a quantity squared. For us, that means that our left-hand side of x squared minus 6x plus 9 equals to 2 is going to factor as x minus 3 quantity squared equals to 2. I said that we need both of those values from the previous steps. I would need the b over 2a, which was negative 3, and the b over 2a squared, which was positive 9. The positive 9 was what I added to both sides of the equation, but that negative 3 is there to help me factor the left-hand side. Though the left-hand side in this example is simple enough that we could have factored x squared minus 6x plus 9 in our heads. But the whole point is that the left-hand side now factors as a perfect square. That's why this is called completing the square. The addition of this term b over 2a squared gives the left-hand side exactly what it needs to factor as a perfect square. We just have some leftover values on the right-hand side. Now all we have to do is solve for x. We've seen these steps before. We're going to take the square root of both sides and get a solution of x equals to 3 plus or minus the square root of 2. So this is the method of completing the square. We have taken a transformative process that takes a quadratic equation like the one we started with, so that the left-hand side factors as a perfect square, and we've got some numeric leftover values on the right-hand side. And then we can solve for x by simply taking the square root of both sides. And really quick, let's talk about any kind of indicator of having no solution. Suppose that the problem that we started with after completing the square landed us at the equation x minus 3 squared equals to negative 2. This is going to have no real solutions, because I can't square a real valued quantity and get negative 2 as an answer. And because I have negative 2 on the right-hand side, I can't take the square root of both sides and expect real valued answers as a result. Therefore, if you complete the square and your right-hand side is equal to a negative number, we get to say there are no real solutions. Let's jump right into another example. We're going to solve the quadratic equation 2x squared plus 7x equals to 15. It's not hard to check that the AC method fails here, so this is not going to factor. First, let's record our coefficient values. A equals 2, B 7, C negative 15. And then let's compute the term b over 2a squared, which for us will become 7 divided by 4 squared, which is 49 over 16. The given equation is in standard form, but we need to move the constant term to the right-hand side. So we'll add a 15 to both sides and get 2x squared plus 7x is equal to 15. Here, since a is not equal to 1, we have to divide both sides by a. In this case, we'll divide both sides by 2 and get x squared plus 7 over 2x equals 15 over 2. The thing with these kind of problems is that you're not guaranteed integer coefficients throughout the process, so we are having to learn how to juggle a little bit with fractional coefficients. But now that we're here, we are going to add our b over 2a squared term to both sides. So we'll get x squared plus 7 over 2x plus 49 over 16 equals 15 over 2 plus 49 over 16. We'll have to simplify the right-hand side into one fraction, and then we're going to have to factor the left-hand side. But recall that we have a factoring formula. The b over 2a term before we square it was 7 divided by 4, and we're going to use that to factor the left-hand side. Our formula says the left-hand side factors as x plus 7 over 4 quantity squared. And our right-hand side reduces to 169 divided by 16. I strongly encourage you to use the factoring formula given to us on the previous slide, because quantities like our left-hand side are hard to factor in your head, but we have a nice factorization formula that always works, that is designed to work. But now that our left-hand side is a perfect square, we will take the square root of both sides. This is going to land us at the quantity x plus 7 over 4 equals plus or minus 13 over 4, because the square root of 169 over 16 is plus minus 13 over 4. Then as we solve for x and combine our fractions, we'll get that x is equal to negative 7 plus or minus 13 divided by 4, and this represents our solution set for this quadratic equation. So completing the square is a very methodical and step-by-step process, and even though sometimes we have non-integer coefficients, it always works the same, and we do have a nice factoring formula. The method of completing the square is important, and it will show up a couple of times in our later sections. But we can do a little bit better or be a little bit more efficient about it by deriving what is called the quadratic formula. If we complete the square on the generic polynomial ax squared plus bx plus c equals to 0, we will find that the solutions are presented as x equals to negative b plus minus the square root of b squared minus 4ac over 2a. This is a formula that all of us have encountered in a math class before. If you want to see the details of how it's derived, please see the last page of the notes corresponding to this video to see the full scope of details. But again, all we're doing is just completing the square on the general quadratic ax squared plus bx plus c equals 0. But with this formula, we can simply plug in the coefficients of a polynomial equation written in standard form and find its solutions. Let's solve the equation x squared plus 8x plus 15 equals to 0. This polynomial in fact does factor as x plus 5 times x plus 3. So you can check on your own that the solutions will be negative 5 and negative 3. But let's see if the quadratic formula agrees with that. Plugging in the coefficients, we'll get negative 8 plus minus the square root of a squared minus 4 times 1 times 15, all divided by 2 times 1. Note that we're only plugging in coefficients. It's a common mistake that some people have plugged in coefficients and variables into this formula, but I'm only plugging in numbers. Using the order of operations, I'll start to simplify all the values. This becomes negative 8 plus minus the square root of 64 minus 60 over 2, which will then turn into negative 8 plus minus the square root of 4 over 2, which is simply negative 8 plus minus 2 divided by 2, which then reduces to negative 4 plus or minus 1. This means my solutions will look like negative 4 plus 1, which gives me minus 3, or negative 4 minus 1, which gets me negative 5. And like I said at the start of this problem, if we were to have factored this quadratic, these are exactly the same solutions we would have gotten. In general, it is better to see if your polynomial factors before you plug things into the quadratic formula, because factoring typically is an easier and a cleaner process. So the idea is that the quadratic formula always works, factoring sometimes works. Next, take the equation 2y squared plus 4y plus 2 equals to 0. This does not factor with the AC method, so I need to use the quadratic formula. But if I plug in my a, b, and c coefficients into the quadratic formula, I will get the solutions y equals negative 4 plus minus negative 16 over 4. So that term underneath the radical, that b squared minus 4ac, in this case produced a negative value. So we would say that this quadratic has no real solutions. However, we can still express these solutions using these things called imaginary numbers. The imaginary number I is defined as the square root of 1. This number comes from the set of complex numbers, which is a bigger set than the real numbers. But this allows me to express my solution set as complex numbers. What I'm going to do is take negative 4 plus minus the square root of negative 16. I'm going to pull that negative 1 outside of the radical and replace it outside with the letter I. So by taking that I outside, I have the square root of positive 16, which I can reduce to the number 4. So after I've done that, and I've done a little bit more algebra, I'll get a solution set of negative 1 plus or minus I. So you may encounter problems like this that have complex solutions, and if you do, this is how they're expressed. You simply take the negative out of the radical and put an I in front of it, and then you reduce the rest of it using algebra. The last topic of this video is something known as the discriminant. The discriminant is the value underneath the radical in the quadratic formula, and this is just used to count the number of real solutions a quadratic has. It doesn't tell us what the solutions are, it just tells us how many there are. So in our first example on the previous slide, we had a discriminant of positive 4. So case 1, if your discriminant is a number bigger than 0, then you get 2 real solutions. If your discriminant is equal to 0 itself, you have 1 real solution. But if the discriminant is less than 0, like it is on the example in this slide, in our case the discriminant was equal to minus 16, then you have no real solutions. So if you get a problem that asks how many real solutions a quadratic has but doesn't ask for the solutions themselves, you can take this shortcut. You simply compute the discriminant just to say I have 2, 1, or no real solutions based on whether your discriminant is positive, 0, or negative respectively.